right, everybody, welcome back to 3.2 part 2 video. This is examples 4 and 5. So, on example 4, first thing we need to do, factor. We have 3 terms, so we need a product of 16 and a sum of -8. That would be -4 and -4. X minus 4 times x minus 4. In the denominator, we have a difference of squares, x squared minus 36. Take the square root of each side. It's x plus 6 times x minus 6. Now, we do have a squared factor in this numerator, so we'll write it as a squared factor over x plus 6 times x minus 6. And this is completely factored form. Now, there are no wholes here because there was not a factor that divided out. For roots, we would set the numerator equal to 0. That's x minus 4 equaling 0. X equals 4. So 4, 0 is the root. Go ahead and plot that point on the graph at 4, 0. Now, what happens here, this mult is for multiplicity. This is a double. This is a squared factor. It is a double root, which is going to give us a tangent at that root 4, 0. We will have the tangent bounce at 4, 0. For asymptotes, vertical asymptotes, we need to set the denominator equal to 0. X plus 6 equals 0. X minus 6 equals 0. So we have vertical asymptotes at x equals 6 and x equals -6. So go ahead and graph those. Remember to graph those asymptotes at dashed lines. It's 4. Now, in behavior, we have a degree of 2 over a degree of 2. So these are the same. So we will play the coefficient game. 1 is the coefficient in the numerator. 1 is the coefficient in the denominator. So when we divide those, we get y equals 1 over 1 or y equals 1 as that horizontal asymptote. Y equals 1 will be your horizontal asymptote. To find the y-intercept, we want to set x equal to 0 and solve for y. We'd use the unfactored form. So we'll get positive 16 over -36. We can divide both of those by 4. It's going to be 4 over 9 negative. So 0, -4 over 9. Set y-intercept. So we're half. 4 over 9 is really close to half. So there's our y-intercept. So we have 2 asymptotes vertical. We have 1 horizontal. And we have a couple points in between. Both of these points being in that middle section, that's the only place the graph can cross the x-axis. And where it does cross the x-axis, it bounces on that x-axis. So from this x-intercept to the y-intercept, it connects. We have to keep going down because we can't cross the x-axis anywhere else. So we keep going down. This is a bounce asymptote, so it doesn't go through and up. It goes back down. So we go back down towards that other vertical asymptote, and this is our middle piece. Now, to find the pieces on the left and right, we have no points, just boundaries, asymptotes, but we do know there is not a together. So on this asymptote at x equals -6, left side, right side, right side. That right side is going down. There's not a together, so that left side has to go up. So we'll come towards the asymptote and we'll come towards that horizontal asymptote. And here's the piece of our graph. Make that not get in the way of everything else. Here's our piece. Okay. At the other asymptote, at x equals positive 6, left side, right side on top and bottom. That left side is going down. There is not a together, so that right side goes up. So close to the asymptote and then towards that horizontal. And here is our function. Its domain is only going to be broken up at the vertical asymptotes. So it will be from negative infinity to negative 6, from negative 6 to positive 6, and from 6 to infinity. In set notation, x such that x cannot equal plus or minus 6. If you wanted to list the plus 6 and minus 6 separately, you can, or you can use the plus minus symbol. So there is number 4, example 4. Let's look at example 5. We want to find all of those things again. So first step would be to factor. On the numerator, we would need a product of negative 14 and a sum of negative 5. There's not a coefficient of x squared, so we can put those factors, those numbers straight into the factors to multiply to negative 14 and add up to negative 5. We need a plus 2 and a minus 7. Then in that denominator, we would need a product of 1 and a sum of 2. And you're thinking, there's no way. But actually, yes, there is. That is x plus 1 times x plus 1. So that is a squared factor in the denominator. So x plus 2 times x minus 7 all over x plus 1 quantity squared. This is simplified factored form. Now, no factors divided out, so there are no holes in our graph. Everything's connected. In the roots, for the roots, we set the numerator equal to 0, x plus 2 equals 0, x minus 7 equals 0. So x would be negative 2, 0, or 7, 0, and none of those are squared, so there's no multiplicity. So we have a root at negative 2, 0, and a root at, so is that 7? Yep. We have roots at negative 2 and at positive 7. Now, for the asymptotes, we set the denominator equal to 0. That's x plus 1 equal to 0. That asymptote is a line. We write it as the equation of the line. X equals negative 1. Go ahead and graph that dashed line on the graph. Now, there is a multiplicity here because this is a double. This was a squared factor. So that makes a together at that vertical asymptote of x equals negative 1. So the left side and right side of this vertical asymptote will come together. The two sides will point the same direction. And we'll figure out what that direction is once we get everything else on here. So the end behavior, we want to look at the degree. In the numerator, we have a degree of 2. In the denominator, we have a degree of 2. That's the same. So we play the coefficient game. Coefficients here are each 1. Y equals 1 over 1. So y equals 1 is a horizontal asymptote. Y equals 1 is our horizontal asymptote here. To find the y-intercept, we need to set the x equal to 0. Use the unfactored form because it's just the constants. So y would equal negative 14 over positive 1. So that point is 0, negative 14, which is a little far off our graph, but we can still plot about where that is. Just go ahead and label that as a negative 14. Estimate it. And this is all we have. So if you're looking at this going, there's no way, well, there is a way. There is a way. And so what we need to do is work on getting all of this stuff connected. Okay, on this right-hand side, we do have two intercepts. We have an x-intercept and a y-intercept. They have to connect. We cannot cross a vertical asymptote. The only place we cross the x or y-axis are at those blue and green dots. So from the blue dot to the right, we will approach that end behavior, that horizontal. From the blue dot to the left, we curve down. We have to go through that y-intercept. Don't hit the y-axis too early. Don't try to drag it way over here. It's not where the y-intercept is. Okay, the y-intercept is down here. So graph will go down. Okay, it'll go down towards that vertical asymptote. Now, we have a together at this asymptote. Right side is already going down. Because of the together, that left side has to go down as well. So from this root at x equals -2, we have to go down, 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 but not crossing that asymptote, staying really close to it, but not crossing it. Then on the left of that root, we would go towards that horizontal asymptote. And this is your graph. Its domain is only broken up by the vertical asymptote. So it would be from -infinity to -1, and then -1 to infinity. In set notation, that would be x's such that x cannot equal -1. And there's your domain. So there is graphing rational functions. There's all of your examples. Thanks, y'all. See you next time.